All right, okay, welcome back everyone. So I'm Sebastien Bubeck, and my job is to teach you about convex optimization. So let's get right into it. Okay, so this will be lecture 1, Introduction to Convex Optimization. Okay, so what are the objects that we're going to look at? So the first object is just a convex set. So let K be a subset of n space, of R to the n, be a convex set. Okay, so again, what is a convex set? You all know it's a set such that if I take 2 points in this set, and I take the segment whose endpoints are those 2 points, then the whole segment is in the set. Okay, so that is for any x, y in K, and for any gamma in 0, 1, we have that the segment, the point 1 minus gamma x plus gamma y is in K. Okay, so this is like maybe this is x, this is y, and this is 1 minus gamma x plus gamma y. Okay, this little point. So that will be one of the main objects. The background is this convex set, but there will also be a convex function. So let f from K to R be a convex function. So what is a convex function? A convex function is like this. It's a function such that if I take any 2 points, so this is the background set, if I take any 2 points x and y, then the function is below its chord. Okay, so this is the chord. This is a linear function that interpolates between the value at x and the value at y, and the convex function is always below this chord. Okay? So again, what I just said is with this same assumption, we get f of 1 minus gamma x plus gamma y. This is smaller than 1 minus gamma f of x plus gamma f of y. Okay, so again, if I have this point here, which is 1 minus gamma x plus gamma y, then this value is, on the y-axis, it's 1 minus gamma f of x plus gamma f of y, and this should be above this function. Okay? So we will use many other formulations of convexity. So let's see one very simple one, which is about the gradient. So how am I going to make appear the gradient out of this inequality? I will just take gamma to go to 0. Okay? You see that if I take this point and I bring them closer and closer to each other, then what I'm going to get is just the derivative here at this point. Okay? Or if you want, you see when I bring this point x towards y, this function is going to go eventually to the tangent. Okay? And this tangent will be a lower bound on the function. So let's see that. So in particular, this implies the following things. So this implies if f is differentiable, then what? Then we have the following. Let's take, let's put the f of x on the other side. So we get f of 1 minus gamma, and let's write it differently. Let's write it as x plus gamma y minus x minus f of x. This is smaller than gamma f of y minus f of x. Right? So when I normalize, okay, so if I normalize, I get this divided by gamma. Okay, so I can remove the gamma on this side. So I get f of y minus f of x is bigger than this thing. And what does this tend to when gamma tends to 0? Well, this exactly tends to the derivative of f in the direction y minus x. Okay, so this is exactly grad f of x inner product with y minus x. Okay, so what we get, let me just rearrange the inequality, we get that f of y is bigger than f of x plus grad f of x inner product with y minus x. So what is this? So this as a function of y, it's f. And what is this as a function of y? This is exactly the linear function. This is the first order Taylor approximation of the function at the point x. Okay, so here I have my point x, and I look at this function. So this function is exactly f of x plus grad f of x inner product with y minus x. And what we just proved is that this is a lower bound on the entire function. Okay, so that's a convex function. Very good. So now what are we going to talk about in this lecture? So we have a convex set, we have a convex function, and what we want is to minimize this convex function subject to this convex constraint. So the goal of the entire course is going to be the following: find, and I need to make precise what I mean by find the argmin of f of x with x in k. Okay, so that's what we're going to be talking about. Okay, algorithms to do that. So for this to make sense mathematically, I need to make clear how do I specify f and k. Okay, so question: how are f and k specified? Right? Eventually, what I want to do is I want to have an algorithm. I want to write specific functions and specific convex set, and I want to have an algorithm that I can run on my computer that will output one point in Rn, okay, which should be an approximate minimizer of this function. So how do I specify f and k? This is very important when I want to get into actually giving an algorithms. So what we're going to mostly talk about, so there are many ways to answer these very simple questions, and they lead to different subfields of convex optimization. What we're going to mostly look at in these lectures is the following setting. So we mostly focus on simple k. Okay, so the convex constraint is not going to be a big deal in this course. I will explain by what I mean. So you can imagine that any computation you want to do with k, basically we can do it. So an example of k would be the Euclidean ball, okay, or the simplex, or other objects like that, simple objects. So I will come back to this. And functions f such that grad f of f can be calculated. Grad f of x can be calculated at any x. Okay, so we will focus on convex functions, which maybe we don't know them entirely, but if I ask you at any point what is its value and what is the gradient, I can answer that question efficiently. Okay, so with those two building blocks, we want to build algorithms which are going to be as efficient as possible under certain assumption on the function f. Okay. So this is a general setting, but to motivate a little bit more convex optimization in the context of machine learning, let me give you some examples of that. Okay. So some examples in machine learning. Okay, and what I'm going to explain here will overlap greatly with Rob's course. So hopefully you can get something from the interaction of those two lectures. Okay, so let's start with just regression. Regression/classification. Okay, so what do I want to do here? So I have a data set. So data set. It's a bunch of points AI. So AI is a point in Rn. So this is the image that Rob was talking about, an image of a cat, an image of a dog, etc. And I have a label yi, which is right now not necessarily a +1 or a -1. It could be a real number. Okay, maybe AI is a description of the CV of a job applicant, and yi is a score that I want to assign to this applicant. Okay, so this is a tuple, a pair, a couple in Rn times R. And what I want is I want to build a function, as we were doing with Rob, that takes in input an a vector in Rn, and outputs a y, which should be close to what this map would do. So find a rule that assigns y to a. And what we're going to look at are linear rules. Focus on linear rules. So what do I mean by that? The picture is like this. So I have my space. This is Rn. Okay, so this is Rn. And I have a bunch of points here. These are my the CV of my applicants. And I have some humans that reviewed all of these CVs and assigned them scores. Okay? So this got this score, this guy got a super high score, this one was not very good, and so on and so forth. Okay, so I have all of these points. So now I'm in dimension n+1. And what do I want to do? I want to fit a linear function that goes through these points. Okay, that's linear regression. And once I have this linear function, what can I do? I can do the following. If I get a new CV here, I can assign it a score just by looking at the value of this function. All right? So how do I do that? So again, so tentative function is going to be a map that maps an A in Rn to a linear function, so that's a linear product x dot A. Okay? This is a point in R. Okay, so this is parameterized by x. X is my linear function. Okay, so tentative function parameterized by x in Rn. Okay, so my predictor is just specified by a vector in Rn. That's my predictor. And this is my tentative function. Once I have specified x, how am I going to classify, how am I going to score my new points in Rn? I'm just going to take the inner product. Okay, so this is exactly trying to fit this linear function that goes through these points with the added constraint that at 0 it's 0. All right, there is no bias term. How am I going to evaluate how well I do? I can just evaluate for this x, how well does it fit all of those data points? Okay, so evaluation is the fit on data, which I will define like this. It's 1 over m. Let's say I have m example. The sum for I equals 1 to m of some loss function of x dot ai yi. Okay, so this is some loss function. So the loss function just specified, if I said 3, but the truth was 2, how much do I pay? Okay, if I said 2.1, then the truth was 2, how much do I pay? Okay, so we have flexibility in designing this loss function. This is so far not given by the problem. We can design anything. Okay, so the most famous one is least squares. So least squares it corresponds to the loss function. L of a pair uv is just u minus v squared. Okay, so it's just, I look at the mistakes that I made. I wanted to predict 2 and I predicted 2.1. So the price that I pay is 0.1 squared. Okay, 0.01. It's some pretty arbitrary choice, right? I mean, I could have chosen absolute value, whatever. I could have chosen other things. But let's see already one very good thing of this loss function. The map x maps to f of x, which is the empirical loss. So 1 over m, the sum for I equals 1 to m of, x dot ai minus yi squared is convex. Okay, so this is a convex function. So trying to find the best linear function that fits my point where the fit is evaluated with the least squares, this is a convex function. Why? Just because t squared is a convex function, and we just apply a convex function to a linear function, and applying a convex function to a linear function results into a convex function. Okay, these are very, very elementary things that I don't want to write because it's too elementary, but if you don't know it, just do it as an exercise. Okay, so this is a convex function. Of course, it would also be a convex function if I put absolute value here. Okay, again, I have flexibility there. So now let me come back to something that Rob was saying about, making modeling assumptions, that we're not, saying that our data is Gaussian or anything like that. It's true, This makes no assumption about the relationship between yi and ai. But what I'm going to say now is that one way to view this is as a maximum likelihood estimator in a certain model. So making a modeling assumption will result in this loss function. And the reason why I want to make this point clear is because you can get many, many examples of convex functions by making a modeling assumption and then looking at what the maximum likelihood estimator would look like, and it turns out that this problem is a convex optimization problem. Okay, and we're going to see a few examples. So right now we're seeing one in regression. I'm going to talk briefly about graphical models and unsupervised learning, where we're going to see this effect again and again, just to give you some diversity of convex functions. Okay, so that's the plan for the next, whatever, half hour.
And is that, do you know that distribution always exists, or is that an easy thing?
No. So I'm going to write it down right now, and then we can see. So, okay, so how to motivate the loss L of uv equals u minus v squared. Make a modeling assumption. Okay, so here is my modeling assumption. So again, I want to make clear, you can run the algorithm in an agnostic way. You can try to optimize this objective function without thinking about anything. But this objective function is appropriate for this type of model. Okay, so this relationship is important. So make a modeling assumption. So here it comes. So assume that y, so the outcome, is distributed as a Gaussian with mean a dot x and with variance 1. Okay, or even maybe sigma squared. Let's put a sigma squared here. Okay, so given the feature A and given a model x, then I assume that y is distributed as a Gaussian whose mean is a dot x plus a sigma squared, okay, which is the same thing, just to make sure we're on the same page. Y is equal to a dot x plus a Gaussian term, plus maybe, let's write it like this, sigma z, where z is an n01. Okay, so this is my linear model. You see, this is linear regression. You don't make any assumption. This is a linear model where I assume that my response variable y is a linear function of my input variable a up to some noise term. And what I'm saying is when you make this linear model, you immediately get linear regression out of it with this form, y. So what is the likelihood? So maybe let me put a lower bar here to make it clear that this is the truth. Okay, so in Rob's language, this is a target concept. This guy is the truth that was used to generate the data. We don't know it. We're after finding x, which is close to this x lower underscore. Okay, so now I can ask, I get this bunch of A's, pairs A, Y, and I want to know what is the likelihood of a given x. Okay, so likelihood of the data AI, YI, if truth is x. Okay, what is the probability that I observe this pair if this was the truth? Okay. Note that I'm not making modeling assumption on the feature vector. I'm only making a modeling assumption on the relation between the outcome and the input. That's the only modeling assumption that I'm making. So when I say likelihood of this data, I only mean I fix AI. What was the likelihood of observing yi, given that the truth is x? Okay, so this is given by the density of the Gaussian, which is the following. So recall that the density of the Gaussian, so an N01, as density, maybe let me put a sigma squared here and maybe a mu. Okay, so an n mu sigma squared has density of the following form: 1 over square root 2 pi sigma squared, exponential minus 1 over 2 sigma squared, y minus, let's say, x, okay, t minus mu squared. Okay, this is the density of a Gaussian with mean mu. Okay, so the likelihood of this observation is how likely was it to observe a yi if the truth was x. So the mean of my Gaussian is ai dot x. So this is 1 over square root 2 pi sigma squared, exponential minus 1 over 2 sigma squared. Let's see the truth. So we observe yi, and the mean is ai dot x squared. Okay, this was the likelihood of this example. Now, what is the likelihood of my entire data set? If I assume that everything is independent, the likelihood is just the product. So this implies that likelihood of the entire data set is nothing but the product for I equals 1 to m of the following things: of 1 over square root 2 pi sigma squared, exponential minus 1 over 2 sigma squared, yi minus ai dot x squared. Okay, which I can rewrite as I just get this constant, so I get 1 over 2 pi sigma squared to the m over 2, and then in the exponential, I get the sum, so I get minus 1 over 2 sigma squared, the sum for I equals 1 to m of yi minus ai dot x squared. Okay, so here you find the function that I was writing before. You see that the likelihood of my data set, if I assume that things were produced using the predictor x, it would be some constant times exponential minus this sum of squared errors. So if I want to maximize my likelihood, I want to minimize what's inside. Okay, so maximizing my likelihood under this Gaussian model is exactly equivalent to minimizing my least squares error. Okay, so let me say this again. So what we find is maximal likelihood estimator, which we abbreviate as MLE, is equivalent to minimizing least squares fit. Okay, so while it's true that minimizing the least squares fit, you can define it without making any modeling assumption, it does naturally come from an MLE of a certain Gaussian model. Yes?
So, can I interpret at this? We should understand the least square from the perspective of the probability model instead of from a geometric, like the Euclidean distance.
No. What I'm saying is this is one useful viewpoint to generate convex problems and to understand least squares. But the geometric perspective is, of course, also very natural and very nice. But you might want to, what I'm saying is, for instance, if your data set had big outliers, things that don't seem Gaussian at all, then maybe you need to think about, is least squares the most appropriate objective? That's what I'm saying. This is one way to put the spotlight on what are the pitfalls of least squares. It's not saying it's the only way to look at it. Okay, all right, so that's it for least squares. I mean, least squares is a tremendously important problem. It's kind of one of the main applications of convex optimization. So this is actually an example that matters a lot, and we'll come back to it. Let me use the other one. Okay, so now I will just give you a regression, classification, sorry. And then we'll move to matrix type problems. Okay, so classification is the same problem, except that now y is restricted to be in -1, 1. So classification. yi is in -1, 1. Okay, so a natural loss is just whether you classified correctly or not. So of course you're not, you have this linear function. This linear function is outputting a real number. So you're not going to classify +1, -1 with just that real number. What you're going to classify is with the sign of that number. So the loss could just be the indicator that the sign of u is different from the sign of v. Okay, so again, you will come back to this example in Rob's lecture, so I don't want to spend too much time on it. But the linear classifier is just saying, if I predict 0.1, then I say it's a +1. If I predict -0.3, I predict it's a -1. So here, this is a 0-1 loss. It just tells, okay, did you classify correctly or not? What's the problem of this loss function from the perspective of this class? It's not convex, right? It's pretty bad. It looks like this, This is a 0-1 loss, okay, with this threshold like this. So this is non-convex. So what can you do? Okay, one thing you can do is you can try to find a convex upper bound on it. Why does it make sense to look for an upper bound? It makes sense to look for an upper bound because if the upper bound is small, then the thing that it's upper bounding is also small. Okay, that's a pretty natural reasoning. So here is the most popular one from the 90s. This is the upper bound. Okay, just a linear slope that upper bounds it. So this is called SVM. These are support vector machines. So L of uv is just the maximum between 0 and 1 minus uv. Okay, so v is a -1 or a +1. So you see that if they agree and it's bigger than 1, then the loss is 0. Okay, so this is exactly this function. And this is a convex function. Okay, this is convex in U. Okay, and because it's convex in U, why is it convex in U, by the way? Because it's the maximum of two linear functions. Okay, so if you take maximum of linear functions, then you always end up with a convex function. Just this is a picture, right? If you take this, this, and that, then this function is a convex function. Okay, take any number of linear functions, take the maximum of them, this is a convex function. In fact, all convex functions can be written like that. Okay, all convex functions are the supremum of a set of convex functions, of linear functions. Okay, this is convex in U, and again, the real function that we're interested in is the sum of functions like this, where here I have a linear function. Okay, and convex function of a linear function is convex. All right, so now we get a convex problem. Another one is a logistic loss. So the logistic loss is like this. So it's smooth, okay? Instead of being, you see, the problem, one of the problems that we'll see is that this function, while it is convex, it is not smooth. And for optimization, smoothness is going to be very important. Okay, so this is convex in U, but not for later. non-smooth. Okay, so our algorithms that will answer this question from the very beginning, they will be better, we will have better guarantees if the function that we're looking at is a smooth function. And you can already kind of feel it, because if it's a smooth function, then one gradient query tells me about all the gradients surrounding this point. Whereas if it's non-smooth, I query this point, I get a gradient of -1, but I don't know, just next to it there could be a gradient of 0. So non-smooth optimization is going to be more difficult than smooth optimization. Okay. All right, so the logistic loss, the formula is like this. L of uv is log of 1 plus e to the minus uv. Okay, so if uv have the same sign and u is very big, then this goes to infinity, so this goes to 0, so the log of 1 is 0. Okay. So if I correlate, I want to predict a +1, and I predict plus 1,000, then I'm very good. My logistic loss is very small. Okay. Right, so this is kind of, okay, again, I come up with this formula, where does it come from? Okay, it's a smooth upper bound on the 0,1 loss. Very good, but there are many smooth upper bounds on the 0,1 loss. So the point is, again, that the logistic loss, it comes naturally from a model. Okay, so this is equivalent to MLE, maximum likelihood estimator, for the logistic model. What is the logistic model? Which is the following. So the logistic model is like this. So denote P of A to be the probability that of observing a +1 given A. Okay, so again, I don't want to make too many notation, things too precise for no reason. What I'm just saying is, imagine I observe a feature. I'm going to describe a model where if you have a feature A, I'm going to tell you a formula for the probability of observing a 1. Okay, so when I observe the feature A, it's either a +1 or a -1. There will be some coin flip, and this coin flip will have some probability. Okay, and I'm assuming a model for this probability. So what is the model? Let's see if this works a bit better. Oh, yeah. So what is the model? The model is just like this. It's just a log model. So I'm going to assume that the scale of this probability is given by a linear function. Okay, so log of P of A. And because I want something symmetric with P and 1 minus P, I just normalize by 1 minus P of A. This, I assume, it's of the form inner product of X with A. Okay, so instead of assuming that my response is a linear function, which doesn't make sense because my response is a +1 or a -1, I could assume that my probability itself is a linear function, but that also doesn't make sense because a linear function, can take any value between -infinity and +infinity, whereas the P should take value between 0 and 1. So what I'm going to assume is that the scale of my probability is given by a linear function. Okay, so you can easily verify that this is equivalent to P of A is equal to 1 over 1 plus e to the minus x bar dot A. Okay, so you get exactly that this loss function, again, sorry, there is something I didn't say, it's the same as before. The function itself, it's not the likelihood, but it's a log likelihood. Okay, so if I take the log of this, I want to maximize the log of this, so I want to minimize minus the log of this. Minus the log of this is exactly log of the denominator. Okay, so this is exactly log of the denominator. Okay, so I see that the logistic loss fit is exactly the negative log likelihood. Okay, so again, logistic loss is equal to negative log likelihood of logistic model. But the point for us, all of this lecture is just motivation for convex optimization, but the point of us is if for some reason you believe on your data the logistic model is reasonable, and you care about this logistic loss, then you're in better shape for optimization because this is a smooth function. So you're in better shape than this SVM business, which is a bit more agnostic. It doesn't necessarily come from a model directly, but it really comes from upper bounding the 0-1 loss like that. So the problem of this one is that it's non-smooth, so optimizing it is going to take longer. All right? Yeah?
Are you really solving a classification problem here or converting it to a regression problem?
I'm really solving a classification problem. I mean,
Does that make sense?
yeah, I'm not sure how to answer it. I mean, classification and regression is the same thing. Like you have some target and you're trying to, have a function that fits all of those target points. Yeah, I'm not sure how to really make sense of it. Although people do make the distinction between them for some reason. Any other question before I move on to more interesting optimization problem? Okay, so the next one is, so now I move to matrix problems. What I want to emphasize is just that we'll do something very general about convex optimization, but for those specific functions that I just wrote so far, you can write explicit algorithm, try to understand the explicit dynamics. And like if you've heard of the perceptron, that's one example, for this, there are many, many algorithms that you can come up with. But what I want to impress on you is that convex optimization is much broader than this. There are many, many other problems that fit in the convex optimization language that looks very different from what we've written so far. Okay? So let's look at one example, graphical models. So in graphical models, what do you have? You have A1 through AM, which are vectors in Rd. And now you don't have a y. Okay? You just have these points. And what you want to infer is the correlation structure between the variables. Okay? So you imagine each one of these feature vectors, it's d variables, and I want to understand what is the correlation between these d variables. Can I try to predict, the third coordinate using the first two coordinates? Something like that. Okay, so question. Infer the correlation structure of the variables. Okay, you can imagine like limitless applications for this. I don't know, does eating less sugar, is correlated with whatever, losing weight or something, or whatever example you prefer. Okay, so how are we going to do that? Let me start now from a model and see what objective function we get. Okay, so Gaussian model. Yes?
Just make it clear,
Yeah.
A1 to AM are random variables, and they're not a sample.
Very good. So again, there is some issue with the level of details that I'm giving you. I'm trying to be mid between high level and explicit functions. So right at this level, I didn't make any assumption. This is a problem which is given to you. You just surveyed 10,000 people, you got some answers, you want to understand the correlation. This problem doesn't come with IID or anything like that. Then comes, the data scientist to make some assumptions. So the assumption that I'm going to say is that this is an IID sequence from some probability distribution. That's where we are now. Okay, so the Gaussian model is that I have IID samples from a Gaussian n mu sigma squared. Sigma. Okay, so now this is the covariance matrix. Okay, so what is the density of this again? Okay, and again, let me underscore it. Okay, so this is the truth. This is the truth. And the point is, under this Gaussian model, we can answer a question like this. Okay, so here is a fact, is that if the sigma inverse, which is called the precision matrix, if the entry ij of this is 0, then we know that, let's say I have a sample x, then we know that xi and xj are independent conditionally on the rest. Okay, so this is not a course about graphical models, so I'm not going to prove that or explain more than this, but if you have a Gaussian sample, you can look at the inverse covariance, called the precision matrix. If the ijth entry of the precision matrix is 0, then that exactly means that those two variables are independent given everything else. Okay, so if you have measured everything else, there is, no point in measuring that guy if you want to predict, there's no point in measuring I if you want to predict J. Okay, that's kind of useful to know. All right, and let's say this is a satisfying answer to the question we started with. So what is our goal now is to estimate sigma minus 1. Okay, so the goal is, goal is to estimate sigma minus 1. Okay, so what's the density? So density of A1 through AM, if truth is Y, is sigma. So what is the density of this? So let's say we know mu. Okay, so assume, So what is the density of this? So I get the following. I get a 1 over square root 2 pi to the n times the determinant of sigma exponential minus 1/2, and then I get ai minus mu transpose sigma minus 1 ai minus mu. And I get the product of those things because I have assumed independence. So this is the likelihood of my data set if I assume it was generated from an n mu sigma. Okay, so in truth it was generated from n mu sigma under bar, but I don't know sigma under bar. Okay, so let's see what is the likelihood if sigma was the truth. Okay. 2 pi to the d, yeah, I want everything to be in Rn. But yeah, otherwise, yes. Okay, so this is the formula of the Gaussian. So what is the negative log likelihood? So negative log likelihood. And say yeah, whatever. Okay, negative log likelihood. Yeah, negative log likelihood is equal to the following. So I take minus log of this. So I will have a sum of stuff. This is, okay, so maybe I just write it. So what do I get? I get minus log of 1 over 2 pi n determinant of sigma, and this is to the m over 2. And then I get the sum plus the sum for I equals 1 to m, and I get minus log of this, so the minus minus they cancel, plus 1/2, and then I get ai minus mu transpose sigma inverse ai minus mu. Okay, which I'm just going to rewrite like this. So I get some constant, which is this first part, plus m, and this was an m. Yeah, plus m over 2 log determinant of sigma plus 1/2 sum for I equals 1 to m of ai minus mu transpose sigma minus y ai minus mu. Okay, make sure you agree with the formula that I just wrote. Okay, and recall that what I want to estimate is sigma inverse. Right, so let's write this. So I want to write everything in terms of sigma inverse. All right, so I'm going to write this. This is a real number, so it's equal to its trace. Okay, this is equal to the trace. You know, a real number is equal to its trace. So it's ai minus mu transpose sigma minus 1 ai minus mu, which is, you know, the trace, it has this cyclic property. So I can put the ai minus mu transpose on the other side. So this is equal to the trace of sigma minus 1 times, where it's the matrix times ai minus mu transpose. Okay. So let me define, so all of this is equal to a constant plus, let me put m over 2 in front. I get log det of sigma. Here I had the 1/2 which goes in front. I put a 1 over m, and I get the following, plus the trace of sigma inverse times S, where S is a sample covariance matrix. S is 1 over m, the sum for I equals 1 to m of ai minus mu transpose. Okay? Right? Just because the trace is linear, so the sum of the trace is the trace of the sum. Okay? And matrix multiplication is also linear. So I get this formula, which I want everything in terms of sigma minus 1, so let me put a minus and a minus. Right? Determinant of sigma minus 1 is 1 over determinant of sigma. With the log, it puts a minus in front. Okay, so we arrive at the following objective function. So to estimate sigma minus 1 via MLE, maximum likelihood estimator, I want to maximize the negative log likelihood. So I want to maximize the log likelihood. So I want to minimize the negative log likelihood. So I want to minimize over X, which is a PSD matrix. Okay, the covariance is a PSD matrix, minus log det of X plus the trace of XS. So this is a linear function of X. Okay, if I do whatever, 2 times this, you know, whatever. It's a linear function of X. So it's convex. And this is a convex function of X. This is convex in X. So this is not obvious. And you know, in the problem session, you will see a proof of this. But the point is, you see, this is a convex optimization problem. I have a convex function, and it's subject to a convex constraint, the constraint of being positive semi-definite. Okay? So this is a certain convex set, and I'm restricted to this convex set in my estimation. So again, the point is, from a data perspective, I collect this data, which I assume to be Gaussian. I compute the sample covariance. Okay, so this is my sample covariance. And now to estimate the precision matrix, I just try to solve this convex optimization problem. Let me make a comment about regularization. So comment. If we know that sigma minus 1 is sparse. Okay, so if in your graphical model interpretation you assume that you have a sparse graph, okay, so most things are independent given the rest, then one might add a penalty term which looks like this, plus lambda times the L1 norm of x. Okay, just the sum of the entries of x. This is what's called sparsity inducing. We won't really have time to get into it, but all I want to say is that you have this convex optimization problem, and now you can add various terms to it, you know, to make it, like to kind of help the optimization algorithm get to the truth. If you have some assumptions about the truth, you can just plug them as convex penalty term for deviating from that truth. If you assume that it's sparse, then the L1 norm of sigma inverse should be small. So let's just put a term which says that if you put too many stuff in your matrix, then you didn't get to the truth. Okay, similarly, in regression, so coming back to the previous example, we might add plus lambda times the L1 norm of little x if you assume that you have a linear classifier which only depends on a few of the features. Maybe you can predict well using 3 or 4 features, coordinates. Then you want to have something small. Or plus lambda times the L2 norm of x squared. So this, I think Rob will talk more about it. This has other properties to add this. These are 2 different things that you're trying to do when you add the L1 norm or the L2 norm squared. So I won't talk more about this. But the point is, adding those norms, those extra norms, it has effect in optimization. So this has the effect of adding curvature, added curvature. So we already talked about smoothness as an important property. Now I'm adding one more component, which is curvature. So if your convex function curves a lot, which is going to be the case with an L2 norm squared, then optimization is also going to be easier. Okay, so what I'm saying is that there are many, many perspectives on those objective functions that we're writing. One of them is that we're adding terms to make it more faithful to the data assumptions that we have. Another one is that we can add terms to make the optimization be easier. And sometimes both work together, and then you're very happy. All right, I'm going to end with one last example in a different, for a different problem, which is unsupervised learning. Is there any question on these graphical models? It's kind of a crash introduction to graphical models, but. So the last example, it will be again a matrix problem. And one of the main things that I want you to take away from it is that when I will write it, it doesn't look at all like something convex is going to come out of it. Okay, so what I want to say is that sometimes there is hidden convexity to a problem. Here, with some experience, you can see convexity coming just because you have a Gaussian. And lots of things are convex with a Gaussian. But what I'm going to write now is different. Okay, so 3 is clustering. Okay, so there is a trend in my examples. I started with the AI YI, then I dropped the YI. Okay, so now here it's unsupervised, I don't have a label. Now I'm also going to drop the AI. Okay, so now all you're going to observe is a graph of interaction. Okay, so data is a graph of interactions. Say the Facebook graph, you just see people who is connected to each other. G equals VE. Okay? And what do you want to infer? What you want to infer is some clustering of the people, of the vertices. Okay, so question, infer some partitioning of the vertices. Okay, and let's make it simple. We just want to partition them into two groups. Okay, so we have this graph of interaction, and we want to separate them into two groups. That's the problem. Okay, that's what whatever your boss told you to do. You get this big graph, and you have to output two groups. You know, the people who like bikes and the people who don't like bikes, something like that. All right. So again, what I'm going to do is that I'm going to make a model. I'm going to make maybe the simplest model for, you know, a hidden partitioning of the vertices. So modeling assumption. This is what's called the stochastic block model. And it goes like this. So there is a hidden partitioning. Sigma, which is in R to the V. Okay, so sigma, which is in -1, 1 to the V. Okay, so to every vertex, I assign a label -1 or +1. Okay, it's either in one group or the other. And I don't know this hidden partitioning. This is my modeling assumption. There is such a hidden partitioning. Now, given this hidden partitioning, how is the graph generated? The graph is generated at random. Then NG is generated from the following. So I is connected to J with probability P if sigma is equal to sigma J, and Q otherwise, and things that Q is less than P. Okay, so if you have two people in the same group, they connect with probability P. And if you have two people in different groups, they connect with probability Q, which is smaller than P. And all of these connections happen independently. Okay, so, and all connections are independent. Okay, it's just a bunch of, you know, it's a very, very unrealistic model, but it's a start. Then what happens? So now the question, as with all of these examples, is if I want to find this hidden partitioning, so let me guess some hidden partitioning, what is the likelihood of my graph given this hidden partitioning would be that? Right. This is the question. Just have to write this thing. So what is the likelihood of X, and maybe let me just say that V is of size n. Okay, I had n vertices, so -1, 1 to the V is really -1, 1 to the n. So likelihood of X, a vector in the binary cube -1, 1 to the n. Okay, so if I guess this partitioning, what is the likelihood of my graph? Okay, so let me sum over all pair of vertices. What do I get? So if I look at xi times xj, just like before for binary classification, you look at the product to get the sign. So if xi and xj are assigned the same group, then this is a +1. If they are assigned different groups, then it's a -1. Okay, so 1 plus xi xj over 2, this is 1 if same group, and 0 otherwise. Okay, so this is kind of my indicator of being in the same group or not. And the other term is 1 minus xi xj over 2. So this is going to be 0 if they are assigned to the same group, and 1 otherwise. Okay, if they are assigned to the same group, then I get a 1, so 1 minus 1 is 0. If they are assigned to different groups, then it's a -1, so 1 minus -1 is 2, 2 over 2 is 1. Okay, so those two numbers are just ways for me to write an indicator of being in the same group or not, assuming that the partitioning is given by x. So for if I have two vertices and they are in the same group, then I get two terms. If they are connected, so let me write aij is the indicator that I is connected to J. Okay, so A is what's called the adjacency matrix of my graph. Okay, so it's just a 1 if they are connected and 0 otherwise. So if I have two guys who are connected, and I assign them to be in the same group, so I have this, +1, +1, and this is there. What's the likelihood of this? This is P. If I have a +1, and no edge, then the likelihood of this is 1 minus P. Right? If I have an edge, and they are in the same group, then it happens with probability P. If I have two guys in the same group and there is no edge, this happens with probability 1 minus P. So what I get here is P times Aij plus 1 minus P times 1 minus Aij. And yeah. And when they are in different groups, instead of P, I have Q. So now I have Q times Aij plus 1 minus Q times 1 minus Aij. Okay, so this formula that I wrote, you can just verify maybe after the class. If you didn't follow, this is exactly equal to, yeah, it's equal to the likelihood of observing this graph G if X was the truth. Okay, there should be a product. Is that why you're not happy? Yes, there is a product, but we're going to look at the log likelihood. Okay, so it's going to change. Yeah, okay, let me, because you're not happy. This is a product. Okay. So what do I find when I take the log likelihood? So log likelihood. Oh, I'm already over time. So log likelihood is going to be of the following form. So what do you see? You see that you have the xi xj times aij, and here you have minus xi xj times aij. Okay, so you have a p minus q times xi xj. And in front of the 1 minus aij, you have the same thing with 1 minus p, 1 minus q, which is exactly minus p minus q. So what you can find is the log likelihood is exactly a constant plus the sum over ij of xi xj times bij, where bij is 1 if I is connected to j, and minus 1 otherwise. Okay, you just get a bonus plus a constant here. You just get a bonus if the two are in the same cluster, and you get a malus if they are not in the same cluster, right? Which makes a lot of sense. If you have two people who are in different cluster and there is an edge in between, it's less likely than if they were in the same cluster. Okay, so let me rewrite this and finish here. So the point is you can rewrite this exactly as, again using the same trick, as the trace of B times XX transpose. Okay, so now what do you want to do? You want to minimize, or maximize in this case, because it's really the log likelihood, you want to maximize the trace of B times XX transpose over X in minus 1, 1 to the n. Okay, and here you're not happy for many reasons. But the main reason is that this is a discrete set. It's a discrete hypercube. Okay, so this is not a convex set. This is not a convex optimization problem. Okay, non-convex constraints. But what you can do is that you can relax it. Okay, so you can have a bigger set. You have this, complicated non-convex set, but you're going to include it in a bigger convex set. And you're going to do the optimization over this bigger convex set. So again, this could be an entire, just like the graphical model could be an entire course. The thing that I'm going to write could be also an entire course, which is just that this is upper bounded by the maximum over X, which is now a PSD matrix of the trace of B times X. And I'm going to add something. So I'm just replacing little x transpose by a capital X, which is some matrix, and I'm going to optimize over capital X instead. What do I know? I certainly know that capital X, this thing is PSD. But I also know this constraint of having coordinate size of minus 1 or plus 1. So it means that this matrix, on the diagonals, it has only ones. So let me throw this in as a constraint. xii is equal to 1. Okay, so this is called the semi-definite relaxation of this combinatorial problem. But the point for us is that this is convex. Why is it convex? I'm looking at a linear function, so maximizing a linear function, that's fine. This, we already said it's convex, okay? The cone of positive semi-definite matrices. And now what am I doing? I'm just intersecting this cone with a subspace. The subspace of all the matrices whose diagonals are all ones. So if I have a convex set and I intersect it with a subspace, I get a convex set. So this is a convex optimization problem, which looks different from the other ones. Okay, so that's all I wanted to say for the motivation of convex optimization. I hope you see that it comes up in many different contexts, and tomorrow we're going to analyze the most basic algorithm, which is gradient descent.